Thanks for the introduction. Thanks for having me here. As Felix just said, I will talk about the classical problems from statistics, but revisited from a more recent angle. And first of all, this is work that I did together with Sjoerd and Holger, who are both here. And it has been done the last 2 years. And now we are finished and fine with it. So since I'm not assuming that all of you are perfectly familiar with the problem of covariance estimation, I will start just with giving you some preliminaries on that problem and also on quantization, and then I will discuss the results that we obtained. So first of all, covariance estimation is a very simple problem to state. Basically, it means given some unknown high-dimensional probability distribution, can I use samples to get information on the covariance matrix? And the covariance matrix is an interesting object because it contains important information on the geometry of the probability distribution in space, which can be used, for example, for data analysis or things like that. So given such a random vector and samples from that, the main question is, how many samples do I need to get a good approximation of sigma? And good means, well, it should produce a small error in some suitable norm. And for us, the main norm of interest is the operator norm. So, as I already said, the covariance matrix contains a lot of information about the probability distribution. So applications for this problem range over different fields like signal transmission, like financial mathematics, or also pattern recognition. And some very common assumptions to simplify the technical details are that we say that X is a mean zero vector, so we don't care about estimating the mean beforehand, which means the covariance matrix has a simple form, and we get i.i.d. samples. Okay, this you can keep in mind for the rest of the talk. This won't change. Good. What do we know so far, or what has been known so far? A natural estimator for estimating the covariance matrix is just a sample covariance matrix. So I take outer products of my samples and average them. And in fact, this estimator already yields good results if I have nicely concentrating distributions, like, for example, Gaussians. So if I have an unknown Gaussian vector and I want to estimate the sigma, I can just use this very simple sample covariance matrix, and the type of result I can get looks like this. So it depends on the operator norm of sigma, and it has two tails. So one sub-Gaussian and one sub-exponential tail that somehow determine how the number of samples influences the error I get, or I can expect. And as you can easily see, the dominant term is the first one. So if I want to reach an approximation of epsilon with high probability, then I need something like epsilon to the -2 times p, which is the ambient dimension samples. And this is what we would expect. P is the degrees of freedom of the problem. So the number of samples should also scale like that. Now, of course, this is a very simplified setting, having only a Gaussian distribution. There exist more sophisticated estimators that also work for heavier tailed distributions. And you can also introduce structure to the sigma and reduce the number of samples that you need. So it doesn't need to be P. If you have a sparse covariance matrix, it will be something depending on the sparsity. If you have a low rank covariance matrix, you can adapt the estimator and get also there the rank influence. What now we were interested in was what happens if we don't get the full samples. Because especially in applications like signal transmission, you need to transmit data and to digitalize it, which means you have to cut off information. And a quantizer would in this case be an additional function around the samples, which maps. And we looked at component-wise mapping. So each component of the sample is mapped to a simple alphabet. And examples for that could be you round to a finite number of digits, or in an extreme case, you even go to 1 bit per entry. And this is in fact the thing we want to do here in this talk. We want to look at this very coarse quantization. So we lose a lot of information, but we wonder how much can we still reconstruct from that. And it's commonly known under the name 1-bit quantization. And you see the Q is not even a continuous function. So it is rather a nasty object. So these are two problems. We have the covariance estimation, we have quantization. Now let's combine them. And in the first case, we really start with only 1 bit per sample, and say we use this very naive quantizer. So we only take the sign of each entry, either +1 or -1, and this is all information that we have. And we have n samples, and each sample is a vector in p dimensions. So two assumptions that we need in this case is, first, we are looking only at Gaussian distributions, which is of course a strong reduction of possible cases, but for the beginning, it is nice as a showcase. And the second thing we need is that the diagonal of sigma is constantly 1. And the reason for that is that the sign quantizer basically loses any scaling information. So the variances of the distribution, which are in the diagonal of sigma, they determine how far it spreads, and this scaling information gets lost by the quantization. So in fact, we are rather reconstructing correlation matrices in this setting. Okay, so what do? We just copy engineering literature, because there it is well known that in such a setting, you apply this estimator. On first sight, this looks a bit strange. So you take kind of the sample covariance matrix of your quantized samples, you rescale it by a different factor. So instead of 1 over n, you use p over 2n, and then you take the sign function of that. Now you might wonder, where does this come from? And the answer is that if you just take the expectation of the inner part, this is exactly arcsine of sigma. And although it's not that simple, you can see if the n goes to infinity, the inner part converges to this, and since sine is a continuous function, you end up with the sigma you want.
So yes. The signs here is a matrix power series or entry-wise?
It's entry-wise. Good question.
Okay.
Yeah. So the functions here are all applied entry-wise, the signs and the signs. if you can distinguish this when I say it. Right. Okay. So what our goal was in this setting, not to invent something completely new, but really mathematically understand in a non-asymptotic way, what happens here.
That question?
There's a question. Yes.
Yeah. Please, can you come again with an intuitive explanation of the 1-bit samples, please?
You mean an explanation of this here?
Yeah.
So why this expectation looks like that?
Yes.
And basically, it depends on the Gaussian assumption. So for Gaussians, you can just calculate that. For example, you find that in Roman Gashinen's book of high-dimensional probability theory. It's named Grothendieck's identity.
Okay, thank you.
You're welcome. Right. What we now did was giving a non-asymptotic analysis. And what is interesting about it, okay, several things appear here that weren't there in the original result for unquantized samples. But if we simplify it a little bit, then you see the form is very comparable. So you have the subgaussian sub-exponential tail, but here the p vanished, and instead a strange matrix A appeared. And this matrix A is in fact the entry-wise cosine of arcsine of sigma, which has entries that look like that. So they are kind of counterparts to the original sigma entries. And this means the influence of P is now hidden in this matrix A. What is amazing about it is that if you take a sigma matrix that is highly correlated, so a distribution that is highly correlated, this matrix A becomes zero, basically. Which means if you have highly correlated matrix probability distributions, this looks like the one-bit estimator, which has much less information, can in fact outperform the unquantized covariance estimation. And this is what you also see if you look at numerical experiments. So here I just change a varied number of samples and I plot the approximation error in the operator norm. And here you see the ground truth, which has ones on the diagonal as we assume, and everywhere else constant C. And the different plots are now different realizations of this C. And if you have a small c, which means small correlation between the entries, you see that the dashed line, which is the quantized estimator, is less good than the original covariance matrix estimator without quantization. But if you get close to 1 with the correlations, then you see that the thing changes. So the sample covariance matrix without quantization, it loses performance while this estimator gains performance. So it's an interesting phenomenon. And you can imagine that the quantization in this scenario just helps the thing because if there's high correlation of the entries, they are already close to 1. So those sign functions push the thing in the right direction. This can be seen as an intuitive explanation of that effect. Just 2 words on the proof. Basically, the main steps are that you use a Taylor expansion of the sign and do it entry-wise. And then the more interesting part is that what you get is a representation of the error you make as form of a series of Hadamard powers. And this you can then control by doing a lot of technical work on Hadamard chaoses. And here we also had to come up with some tools that hopefully are interesting also for other challenges. But it required a lot of work. What is also hidden in the results that I showed you so far is that our techniques include the possibility to have sparsity as a prior, and then you have kind of masked estimations where you only observe part of the entry, or you are interested only in part of the entries, and then you can also include dependency on the sparsity level instead of the ambient dimension. Okay. And one point I almost forgot, the bounds that I showed you in this theorem, they are basically optimal. So we have the corresponding lower bounds. So this matrix A is not just a proof artifact, but it really resembles what happens there. Now, the problem is, in this simple model, the scaling information is lost. And if you're interested in covariance matrix estimation, you would like to get also the thing if there are variances that are not equal 1. And since for this we didn't find a way, if we only use 1 bit, we increase the number of observation bits per sample to 2 bit. And this we did in a way that is well known in engineering literature as well, but hasn't, to the best of our knowledge, hasn't been used in the context of covariance estimation so far. Namely, we added the dithering to the quantization procedure. So we have now not only our unknown x, but we have in addition 2 designed dither vectors. And for each sample, we draw corresponding dithering vectors. So for sample x1, we draw tor1 and tor-bar1. And then as samples, we get 2-bit samples, once the sign of xk plus tor k and once xk plus tor bar k. And tor and tor bar have the same distribution, but they are independent to each other. And the distribution of those tors is just a uniform distribution on some interval that is characterized by lambda. What do we do in this case? we use an estimator that is much closer to the sample covariance matrix. Basically, we have an asymmetric estimator that takes the outer product of those 1-bit samples, so of the 2-bit samples, one on each side, and takes the average. The only important thing is that we need to scale here with the dithering parameter lambda. And the idea here is, just as an intuition, assuming that x is bounded, so has a bounded distribution that is inside the lambda cube, this becomes an unbiased estimator. So in some sense, on a region that is controlled by lambda, this thing is an unbiased estimator, and then one only needs to control what happens outside of the lambda cube. And what we got, again, here you see it written for subgaussian distributions. If we take samples, n samples, and we have a sufficiently large lambda, then we get certain guarantees. And since, again, they are maybe not that easy to read in this form, let's simplify a bit. If lambda is really of a good order, which depends slightly on the number of samples we use, then with high probability, we get again a bound that consists of the two important tails. You see the p appearing and an additional dependence on log n, which is a very mild additional error. Okay.
So what is the sigma infinity?
It's the max, so the maximal entry norm, yeah. And in fact, if you are familiar with literature on this, the p times sigma infinity norm kind of is not the optimal thing you would expect from Gaussian estimation of via sample covariance matrix. They would rather pop up the effective rank, which is a nicer quantity because it becomes small if you have low rankness. But here we get something a bit worse, so it's still an open question how we can somehow introduce the effect of low rankness. But if you state this result in full generality, as we have in our paper with masked estimation, it resembles perfectly the state-of-the-art masked results by Chen and Trop that were in their paper on masked sample covariance, masked covariance estimation. Yeah. Okay, so how does this compare to the previous estimator? Here you see, again, some simulation. So over the different ambient dimensions so here I vary the p and keep the number of samples fixed. And I again plot the approximation error. And what you see is in blue, the sample covariance matrix without quantization, so on the full knowledge of the samples. Then the orange line shows you the 1-bit estimator that requires the diagonal equal 1. And the green, the 2-bit estimator that has this additional dithering. First observation, you see in this direct comparison that the orange line is very close to the sample covariance matrix. But here you have to keep in mind that for a fair comparison, the sigma has 1s on its diagonal. So here, this orange line has so the 1-bit estimator has an advantage because it is perfectly fitted to that scenario. The dithered estimator comes quite close. And one aspect here is it's hard to compare the 1-bit and 2-bit estimator directly in a fair way, because either one has the 1-bit estimator has an advantage because of the 1 diagonal, or the dithered estimator has an advantage because the 1-bit estimator cannot estimate a non-constant diagonal. So it's not that easy to compare those two fairly, but in a fair way. But what you see is that both of them give reasonable results in the settings. The green depends very much on the choice of lambda. This is what the right plot shows. So here you see the same thing for a fixed dimension over different values of lambda. So how you choose the dithering. And there is certainly a sweet spot for tuning this parameter. And this is also an interesting question for the future, whether there is a data-dependent way to tune this lambda. Proof sketch, again, just in 2 lines. Basically, the first thing one needs to do is to understand how lambda controls the bias of this estimator. So I need to make lambda sufficiently large to control the main bulk of my distribution in an unbiased way. And I need to find a trade-off between controlling this and having only a small rest of not so well-controlled things. And then basically applying an LQ version of Bernstein to control the moments of the error. And then you get a high probability bound. Again, some additional insights. The same result we got in a more general form for masked estimation. So again, introducing sparsity to the thing as a structure. It is possible to get not only subgaussian, but also sub-exponential or even heavier tailed distributions in the result. The thing what you then pay is that you raise the log n factor in the result to the power of the tail that you want to have. So also here, there's kind of a trade-off at the moment. And we have corresponding minimax lower bounds. So it is the estimator is optimal. So the estimates we get are optimal in that sense. Final conclusion, depending on sigma, you can really get the same performance of estimation, even though you throw away a lot of information. So you only keep 1 bit per sample or 2 bit, but you get very, very reasonable results. But of course, there are cases where you suffer loss. I showed you one where the covariance, the covariances between entries were rather small for the 1-bit estimator, and for the 2-bit estimator, a case that is harder to handle is if there is a very peaky diagonal, because it somehow uses the same lambda over the whole diagonal, which means the dithering will only be good for part of the variances and lossy for the rest. Yeah. So I mentioned some of those questions already. We would be interested in also cover other types of structure in these results. We would be very interested in auto-tuning the lambda. I guess this is the greatest obstacle to just making it applicable in an easy way. And of course, it would be interesting what happens for heavy-tailed distributions. What can one do there? Because the 1-bit quantization seems to be a good way of making heavy-tailed things very compact, concentrated around 0. So it would be also interesting if one can make use of it, even if one is not interested in quantization. Thanks, and I'm happy to ask any questions.